Welcome to the University of Saskatchewan Computer Graphics Course Project Demonstration by Drake Zarowny and Doug Packard. Our project intention was to explore the fundamentals of procedurally generated terrain. Although there are many components to terrain and graphics, we decided instead to focus on subjects related to the generation itself. To generate our terrain, we decided on an algorithm that would be simple in implementation, but would still create terrain that was interesting and complex. The diamond square algorithm was suitable for these goals. We started with a flat mesh, similar to the plane object from the assignment framework. Each vertex you see on the mesh is eventually adjusted by the algorithm. The first step of the diamond square algorithm is the diamond step. A random value is generated at the square midpoint of the terrain. This value is calculated by averaging the four corners and adding or subtracting a random amount. The next step is the square step. The terrain has now been split into diamonds. Again, the center point of these diamonds is calculated through the average of its points and adding a random amount. The terrain now split into squares can go through the square step once more. This process is repeated until the lowest level of vertices is reached. You have now generated terrain. Our algorithm is flexible in that different terrain conditions can easily be created. Producing softer terrain is done by simply reducing the random amount that is added. We continued to modify the diamond square algorithm in order to achieve a set of terrain that gradually increases in height and complexity. We wanted to represent terrain one might see walking inwards on an island. The texture used is a simple gradient of colors, representing the topographic qualities of terrain. The texture coordinates of each vertex are mapped by their respective height. The result is a simple but effective method of showing terrain heights. For convenience, we used a two-dimensional texture that could be modified as needed. In a wireframe view, you can see the staggering number of polygons. We decided that most of these were unnecessary. Neighboring polygons that have little variation in height could be combined into a single polygon instead. In order to do so, we searched for another algorithm that would reduce the number of polygons. The answer we found was a terrain simplification algorithm. It works by splitting the terrain into a number of equal-sized square zones. At the highest level, the potential subzones are checked to see if they have too much vertical variation. Zones that are flat enough are left alone. If a high-level zone has too much vertical variation, it is split into subzones. Those subzones are then checked to see if they should be split as well. Unfortunately, the zones will not always split into perfect variations of triangle squares. Depending on which sides of the zones are flat and which sides have inclines, it is possible that only specific portions of the zone will be split. We therefore produced a set of varying primitives to fill in the subblocks appropriately. Triangle strips and triangle fans are introduced for zones that have uneven sides. You can see the different primitives in action here. Running this algorithm one time can reduce the terrain of 1,000,000 polygons to one that has only a few thousand. However, we wanted to take it one step further and attempt some real-time optimization. Normally, when determining whether or not a zone is flat enough, comparing the height of its vertices is all that is necessary. Instead, terrain that is close to the camera should be generated in high detail, whereas terrain that is far away can have a reduced number of polygons. When checking a zone to see if it should be split, even if a zone has a large height variation, a far enough camera distance will prevent further subzone splitting. You can see in this example that the terrain of several thousand polygons is reduced to 32 evenly distributed zone blocks. The result is that level of detail is high in areas surrounding the camera, but it is reduced in areas outside a specified radius.